Army 13770 is en route IFR from Jacksonville to Cairns Army Airfield, Victor 22 and Victor 7 West. They have just passed Lee intersection south of Valdosta VOR when they learn that weather at Cairns has gone below approach minimums and is expected to continue to deteriorate. They'll have to proceed to Tallahassee, their alternate airfield, for an ILS approach.
Doesn't look like we're going to make it home tonight.
Check it while I do some checks.
Roger, I've got it.
No radar at Tallahassee, but everything else looks okay.
Though this aviator may never have seen Tallahassee Municipal, everything he needs to know to make an ILS approach and landing is provided on this page. Later, we will examine an ILS approach plate, but first we will become familiar with the ground components which make up an Instrument Landing System, or ILS. There are 4 types of components which may be required in every ILS. First, the localizer transmitter. Then the glide slope transmitter, the marker beacons, and the approach lighting system. The localizer transmitter is housed in a small building at the far end of the instrument runway. The equipment operates unattended, and standby units are provided to assure uninterrupted service. Should one unit fail, the standby will take over automatically. The specially designed localizer antenna system is precisely aligned with the center line of the instrument runway. In a sketch, the localizer ground components look like this. The localizer transmitter building is situated off the far end of the instrument runway. By far end, we mean the end opposite the normal direction of instrument approach. The localizer antenna is positioned about 1,000 feet from the far end of the runway for optimum sighting. The antenna produces a beam of radio energy, much like the beam of light from a lighthouse. You cannot see this beam, but your airborne ILS equipment can. The radio guidance beam has 2 signal patterns which overlap exactly over the center line of the runway. When your ILS equipment receives equal proportions of the 2 signal patterns, your course indicator gives a needle-centered reading. Note that there are beams projected in 2 directions from the localizer. One along the center line of the runway, the other in exactly the opposite direction. The guidance beam extending over the runway is called the front course, and the opposite beam is called the back course. Approaches can be made on the back course, but as we shall see, a different technique must be used. Some localizers have back courses which are not usable for approaches. Now let us examine this dual pattern radio beam more closely. The beam produced by the overlap is usually 4 to 5 degrees wide. This provides a runway approach threshold of approximately 700 feet. Localizers usually have a voice capability, which is frequently used for air traffic control instruction. Most localizer signals can be used effectively for guidance for a distance of about 25 miles. In addition to the guidance patterns, localizers continually identify themselves by broadcasting the airport's 3-letter identifier, preceded by the letter I. Use of the localizer beam for approach tracking is relatively simple. The 2 sides of the signal overlap are called the blue sector and the yellow sector. These designations are derived from the dial of the VOR course indicator, where blue and yellow colors are used to identify off-course indications. The colors are arranged on the indicator so that when an aircraft is inbound on the front course or outbound on the back course, the needle indications are directional. An example will make this clear. If an aircraft inbound on the front course moves off course into the blue sector, the needle will deflect into the blue, indicating that a left turn toward the needle is required to return to the course. The same is true when outbound on the back course. You must remember that inbound on the front course or outbound on the back course, you turn toward the needle. In the opposite direction, just the reverse is true. When inbound on the back course, the needle is not directional. If you stray into the yellow sector, the needle will make a corresponding move into the yellow area. But you will have to turn away from the needle to return to an on-course reading. Outbound on the front course, the same rule holds. The needle is not directional. Color indications on your course indicator are always correct, but the needle is only directional when inbound on the front course or outbound on the back course. When learning to use the course indicator, which is used for both VOR and ILS tracking, you must understand how it differs in sensitivity. In VOR tracking, the entire scale equals approximately 20 degrees. However, in ILS tracking, it represents approximately 4 to 5 degrees. Thus, we can see that turns to correct needle deviation in ILS tracking must be small and precise. In ILS tracking, needle response is very sensitive. There is another factor in ILS tracking which must be understood. Recall that the beam produced by the localizer antenna can be used effectively for a distance of approximately 25 miles. 5 miles out from the localizer, the beam's width has increased to more than half a mile. 25 miles out, the beam is well over 2 miles wide. From these facts, we can readily see that the amount of correction required to center the needle depends on how far out you are from the airfield. If you are tracking inbound at a distance of 25 miles, a relatively small needle deviation may require quite a large correction to return to the localizer. However, if you are closer in, the same amount of needle deviation will require a much smaller turn. During final approach, corrections become very sensitive. The point to remember is that out here, a 1-dot needle deviation may mean you're half a mile off track. But close in, the same 1-dot needle deviation will indicate a position only 100 feet or so off track. The localizer gives you an accurate course to the runway. Safe descent is the job of the glide slope transmitter. The glide slope transmitter is housed in a small building similar to the localizer installation, and its antenna is on a short mast nearby. Both the glide slope building and antenna are located near the touchdown end of the runway, but are placed to one side so that they will not cause a final approach hazard. The glide slope transmitter produces a signal which provides a glide path on the front course of the instrument runway. At major airports, there may be an additional glide slope installation on the back course, but this is not common. Normally, the glide slope is elevated 2.5 degrees above horizontal. However, if the terrain rises off the approach end of the runway, or there are other tall obstacles, the glide slope angle may be raised to 3 degrees. With a normal 2.5 degree glide slope angle, the absolute elevation of an aircraft 5 miles out is approximately 1,300 feet. Closer in, at 3/4 of a mile, its absolute elevation is just under 200 feet. The glide slope beam is quite thin. Its thickness is only 1 4/10 degrees. Because of this, you may find that tracking the glide slope requires practice. The indications of the glide slope needle are always directional. Descent below the glide slope will give you a fly-up indication. An ascent above the glide slope will give you a fly-down indication. The glide slope needle is always directional, even on a back-course glide slope. There are several cautions which must be observed in descent on a glide slope. It could be dangerous to descend below the glide slope, particularly when you are quite close in. You can readily see that even a slight drop below the glide slope would bring you dangerously close to the ground. Another caution to take into account is that in addition to the desired glide slope, false courses with non-directional needle indications will be transmitted by the glide slope antenna. If approved procedures are used in intercepting and tracking the glide slope, there will be no danger of attempting to follow a false course signal. One final caution: glide slope indications are only reliable and accurate within the angular width of the localizer beam. Descents on courses other than the localizer course should never be attempted. The glide slope transmitter gives you a safe path of descent to the landing threshold along the course provided by the localizer. Marker beacons provide you with an accurate position fix on your course along the localizer and glide slope. Marker beacon transmitters are automatic facilities housed in small buildings off the end of the instrument runway. A marker beacon transmits its signal in a vertical direction only. The vertical radiation pattern of a marker beacon is elliptical in shape and quite narrow. Because the beam is vertical and narrow, the marker beacon signal can only be received when your position is directly above the beacon. Thus, the marker beacon provides you with a definite radio position fix as you track inbound on the approach. Marker beacons are used to provide a fix at two specific points on the glide slope. One marks the ideal point at which the glide slope should be intercepted, approximately 5 miles from runway. It also serves as the final approach fix for the ILS approach. The other marks the point where an aircraft will be at or near approach minimums. The first marker beacon encountered is called the outer marker. The second beacon is called the middle marker. It is called a middle marker because at some installations you will find a third marker, which is called an inner marker. All the markers can be identified by distinctive audible radio signals. The outer marker identifier is a continual series of low-pitched dashes. The middle marker identifier is a continual series of medium-pitched dots and dashes. The inner marker identifier is a constant series of dots. Almost all outer markers also have a supplementary component of the instrument landing system. It is called a compass locator. The standard symbol for a radio beacon is combined with the standard marker beacon symbol to indicate it. On charts, the abbreviation LOM is used to designate a combined outer marker and compass locator. Compass locators are low-powered, non-directional radio beacons with a range of about 15 miles. The primary purpose of a compass locator is to provide a means of transitioning to the outer marker. The identifier for outer marker compass locators is the first two letters of the basic airport identifier. With a localizer to provide course guidance, a glide slope to provide a safe angle of descent, and marker beacons to provide a definite position fix, the instrument landing system only lacks an approach lighting system to be complete. Approach lights are designed to aid you in establishing visual contact with the runway and completing a visual approach, either in conditions of poor visibility or night or both. This lighting system, called the U.S. Standard A system, has been adopted by the FAA. You will find it on many instrument runways. In standard configuration A systems, white lights extend out from the landing threshold for 3,000 feet. These lead you to an interrupted line of red lights, and finally to a continuous line of green lights which mark the landing threshold. The touchdown zone is clearly defined with bars of white light. And the runway center line is marked with white lights set flush with the runway surface. To help you in locating the landing threshold, this row of white lights is very brilliant, similar in intensity to a photographic flash gun. When seen during an approach, the blue-white bursts of light give the effect of large tracer shells moving rapidly toward the touchdown area. The standard A system will not be found on all instrument runways. However, the instrument approach procedure booklets have detailed diagrams of all common lighting arrangements. These diagrams include a key letter and thumbnail sketch, which will also be found on the approach plate. Thus, you can determine the type of approach lights at any airfield prior to arrival. 3 of the ILS ground components are radio transmitters, which are assigned specific operating frequencies. The localizer and the glide slope receivers share a single control panel. The same ARN30 control panel used for VOR functions is used for ILS. The tuning window shows only the localizer frequency. When a desired localizer frequency is selected, the proper glide slope frequency is tuned automatically. Marker beacons all transmit on the same frequency, 75 megahertz. No tuning is required since a fixed frequency receiver is used. The only controls are an on-off volume switch, a sensing switch which increases or decreases the receiver's sensitivity to improve performance, and a marker beacon light, which provides a visual means of determining marker passage to supplement the oral signal through your headset. Now that we are familiar with the 4 categories of ILS ground equipment, let's return to Army 13770 as they continue on Victor 22. They have checked the weather forecast for Tallahassee and found it is favorable. They have therefore requested change in clearance from Jacksonville Center to land at Tallahassee. Now they receive their clearance.
Army 13770 cleared to the Tallahassee locator outer marker, Victor 22 Tallahassee VOR, direct to the outer marker, maintain 4,000.
Army 13770, roger.
With their clearance secured, the pilot uses the remaining 10 minutes to the Tallahassee VOR to familiarize himself with the ILS approach plate for Tallahassee Municipal. ILS approach plates provide all the information required for a successful ILS approach and landing. The instrument runway number, the radio frequencies. Transitions and minimum safe sector altitudes are given. Army 13770 will approach from the Tallahassee VOR. On this transition, the minimum safe altitude is 1,800 feet. The course is 175 degrees, and the distance is 13.8 nautical miles. The course outbound and inbound is shown in two places, on the localizer track and on the profile view. Also shown on the profile view is the glide slope angle. This figure can be used with the rate of descent table in the front of the Instrument Approach Procedures booklet. For example, using the glide slope angle of 2.5 degrees and a ground speed of 70 knots, we interpolate between 2.4 and 2.6 degrees to obtain the proper rate of descent of 312.5 feet per minute. On the ILS approach plate, you will also find a block listing the appropriate landing minimums for the various categories of aircraft. Also given is approach minimums for approaches without glide slope and for circling approaches. In the lower right corner, a chart shows the time at various speeds from the locator outer marker to the mandatory start of missed approach procedure for approaches without glide slope. Knowing the time from the locator outer marker is always helpful, but it is essential when making an approach without the glide slope. Finally, the ILS approach plate has an airport diagram which shows type of approach lighting system, length and width of runway, location of tower, and other useful information. The pilot should be as familiar as possible with the approach data, and the co-pilot must monitor the approach plate during the ILS approach to provide requested data. They are coming up on the Tallahassee VOR. As station passage is indicated, they note the time and begin their turn to a heading of 175 degrees. The pilot tunes the ADF to the compass locator frequency. He then contacts Jacksonville Center.
Jacksonville Center, this is Army 13770, Tallahassee VOR 15-4000. Estimating the Tallahassee locator outer marker 25, over.
Roger, Army 13770, expect ILS runway 36 approach at Tallahassee. Altimeter 29906, contact Tallahassee approach control 317.4 now.
Roger, altimeter 2996.
On all instrument flights, pilot-co-pilot teamwork is essential, but it is always the pilot's duty to assure that the co-pilot is adequately briefed and ready to assist. As they roll out on course, the pilot switches to the Tallahassee approach control frequency to contact the controller.
Tallahassee approach control, this is Army 13770, estimating the Tallahassee locator outer marker 25-4000, over.
Roger, Army 13770, clear at ILS 36 approach. Weather measured ceiling 400 overcast, visibility 3/4, light rain fog, wind 350 degrees 10, altimeter 29906. Report outer marker outbound, over.
Roger, altimeter 29906. I have the aircraft.
Roger, you have the aircraft.
Tallahassee approach control, Army 13770 is out of 4000.
With approach control contact established, the pilot immediately starts a descent to the transition altitude, 1,800 feet, as shown on the approach plate. The co-pilot tunes the VHF receiver to the localizer frequency. This automatically tunes the glide slope receiver to its paired frequency. At the same time, the pilot adjusts the marker beacon volume control to its midpoint. At transition altitude, the pilot levels off and continues to track inbound on the locator outer marker. He proceeds at 1,800 feet direct to the locator outer marker, where he will turn outbound on the localizer course and start to descend to procedure turn altitude of 1,300 feet. He reports to approach control.
Tallahassee approach control, Army 770, Tallahassee locator outer marker 25, 1,800 feet outbound.
Roger, 770. Contact Tallahassee Tower, frequency 257.8, outer marker inbound.
As the radio is tuned to the tower frequency, the pilot starts his procedure turn to establish himself inbound. When established inbound on the localizer, he descends to 1,200 feet, the altitude at which he will intercept the glide slope. Over the locator outer marker, he contacts the tower.
Tallahassee Tower, Army 13770, outer marker inbound.
Army 13770, clear to land runway 36, report field in sight.
Inbound over the locator outer marker, the pilot notes the time, and at glide slope interception, he starts his descent. Establishing a proper rate of descent is greatly simplified by pre-planning based on glide slope angle and ground speed. Corrections to remain on the localizer and glide slope must be smooth and precise. Concentrated practice will develop this skill. A proficient pilot can keep both needles crossed in the center of the small circle or donut. Work for this kind of proficiency. At this point, the co-pilot's job is important. He must scan carefully to establish contact with the ground as soon as possible. Sometimes you will break out clean under a cloud layer. In other situations, ground fog and rain will give you only fleeting glimpses of the ground. As soon as the co-pilot sees the ground, he notifies the pilot and takes the controls to complete the landing visually. With the field in sight, the co-pilot must take out any crab and line up with the runway as he prepares to land. The pilot reports to the tower.
Tallahassee Tower, Army 13770, we have the field in sight, over.
Army 13770, contact ground control 348.6 from clear of runway.
These are good words to hear when the weather is really messy. The assurance that you can handle an ILS approach anywhere and at any time when minimums permit is well worth working for. ILS will get you to the ground every time if you have the skill. At 11:30 hours on the 22nd of April, an Army aviator signs out for a routine military flight. The logbook of his helicopter indicates that it has been carefully checked and refueled for a 250-mile flight. His navigation charts identify major natural and man-made ground features along the projected route and show where they are located. His flight plan authorizes him to fly by instruments if necessary and directs him to maintain an altitude of 5,000 feet. His flight weather briefing informs him of existing and predicted atmospheric conditions along his planned route. It also provides him with parallel information for an alternate airfield. The meteorological data in this briefing has been selected and put together from an extensive list of teletype sequence reports. These symbols, numbers, and abbreviations represent the latest hourly findings of hundreds of weather stations situated over a large area of the United States, Canada, and northern Mexico. This hour-by-hour updating of weather information is essential because the Earth's atmosphere, in contrast to its landscape, is always in a state of flux. It has ridges of high barometric pressure, troughs of low pressure, areas of heavy cold air, and rivers of wind, but their positions are never the same. There are many kinds of weather maps. They have to be redrawn and reissued several times a day. This perpetual moving and shifting of the atmosphere may seem quite haphazard and unpredictable, but it is actually brought about by certain basic constant factors and principles of meteorology. Every aviator must learn, understand, and put to good use these factors and principles of meteorology. The great envelope of gas we call the atmosphere is the medium in which he operates, in which he carries out his mission. As the atmosphere rises up toward outer space, it forms itself into 4 concentric layers, only 2 of which, the troposphere and the stratosphere, are significant to flying. The lower layer, the troposphere, varies in height from 25,000 at the poles to 60,000 feet at the equator. It is higher during our summers and lower during our winters. This lowest of the 4 layers is particularly well named because the prefix tropo means turning or changing. Air changes within the troposphere result in thunderstorms, rain, and hail. This type of cloud produces drizzle, sleet, and snow. Other atmospheric conditions produce fog and clear skies. The stratosphere, which extends 35 to 50 miles above the Earth, is characterized by stratified layers of air. It is essentially cloudless, and in its lower altitudes, its temperature is isothermal, or uniform, over any given point within the stratosphere. The boundary between the troposphere and the stratosphere is called the tropopause, the zone where vertical air currents cease and weather, as we know it, reaches its upper limits. Both troposphere and stratosphere are composed of the same mechanical mixture of gases known as dry air, consisting of approximately 78% nitrogen, 21% oxygen, and 1% of other gases such as helium, hydrogen, argon, and carbon dioxide. If these 2 adjacent layers of atmosphere have the same basic chemistry, why do we find such a clear-cut difference between them? Why does the stratosphere have no weather to speak of, while the troposphere has so many varieties, both good and bad? The answers to both questions go directly back to the fact that the troposphere is the only layer of atmosphere which is close enough to the Earth to be effectively warmed by the heat which its surface receives from the sun and reflects back into the lower altitudes. This warmth makes the dry air of the troposphere into a sort of gigantic sponge and enables it to absorb and retain considerable amounts of moisture in the form of water vapor. This gaseous mixture of air and moisture is called natural air and exists over every portion of our planet. Whenever the sponge has soaked up all the moisture it can hold at that temperature and additional moisture is added, the water vapor will condense into water droplets. When the temperature is below freezing, the water vapor will sublimate into a cloud composed of ice crystals. This formation of water droplets and ice crystals will never develop unless the atmosphere is pushed beyond saturation. However, there is another factor to consider as well. Smoke, dust, salt, volcanic ash, or other so-called nuclei must be present to provide the nucleus for the formation of water droplets or ice crystals. The maximum amount of water vapor that the air, as represented by this beaker, can hold without condensation taking place depends largely upon its temperature. At minus 18 degrees centigrade, it may contain only up to 1 gram of water vapor. But as the temperature goes up, so does the air's capacity, until at plus 32 degrees centigrade, it may hold as many as 34 grams. As long as the temperature continues to rise, the air will be able to hold more and more moisture. If, however, the temperature starts falling, there eventually comes a point when the air can no longer contain its moisture and saturation takes place, followed immediately by condensation and the development of clouds or fog. The exact point where condensation takes place in any particular weather situation is called the dew point and is identified by a thermometer reading, in this case, 25 degrees centigrade. As long as the temperature of the air is well above the dew point, the skies will remain clear. It is when the difference between these two readings begins to narrow to the vanishing point that the experienced aviator begins to look for danger signals, such as fog, thunderstorms, hail, and snow. Dew point and air temperature are just two of the several readings and measurements recorded in all the thousands of weather stations scattered across the world. This weather station at Cairns Army Airfield, Alabama, is equipped with characteristic measuring instruments. The automatic psychrometer, for example, registers the temperature in Fahrenheit and the present dew point. If this mechanical instrument were to malfunction, or if it were unavailable, the station could use its sling psychrometer. This manually operated instrument consists of two thermometers. One of them is moistened by means of a linen wick. When the air is very dry, evaporation from the wick will cool the wet bulb thermometer, and its temperature reading will be considerably lower than that of the dry bulb thermometer. On the other hand, if the air were saturated, there would be no evaporation, and both the thermometers would therefore give the same readings. Today, however, the atmosphere is quite dry, and the difference between the two readings is nearly 13 degrees centigrade. The actual dew point and relative humidity are then determined by using this computer. The barometric reading is another very important hourly measurement at this and every other weather station. The aneroid barometer, for example, is activated by partly exhausted sealed bellows, which contract or expand with the increase or decrease, respectively, of the surrounding air pressure. It is similar in construction to the altimeters found in all United States Army aircraft. The most common pressure instrument, however, is still the mercurial barometer. Altitude, temperature, and distance from the equator all have a bearing on any pressure reading. Two other hourly weather measurements involve wind direction and wind speed. Wind direction, the left reading, is determined by this exterior wind vane. And wind speed, the other reading, is determined by this rotating anemometer. The faster the wind blows, the faster these three blades will whirl around their axle. At 12-hour intervals, balloons are sent aloft with radiosonde instruments to evaluate current air pressures, temperatures, and dew points at various elevations. Radio signals from these throwaway or expendable instruments are transcribed to atmospheric diagrams, whose graphic displays provide various sorts of pertinent weather information. This includes such elements as cloud layers, potential icing levels, and high altitude temperature readings. In nearly all cases, the radiosonde readings will show a fairly regular lowering or decrease in air temperature as the altitude increases. This progressive decrease has a normal lapse rate of about 2 degrees centigrade per 1,000 feet throughout the troposphere. It is due, of course, to the fact that as the balloon rises in the air, it gets further and further away from the Earth's reflected heat. Occasionally, however, the radiosonde signals register a local temperature inversion, where the air temperature increases rather than decreases. Inversion layers are stable and produce smooth flying conditions within them. But they are somewhat like chimney dampers and prevent the air underneath from rising. This is apt to create a haze condition and temporarily restricted visibility at lower altitudes. Radiosonde equipment registers air pressure as well as air temperature. And as the balloon gets higher and higher, it is normal for the pressure, like the temperature, to get lower and lower. This is due, of course, to the fact that the column of atmosphere above the rising balloon keeps getting shorter, and therefore lighter in weight, causing the balloon to expand during its ascension. Every weather map shows pressure and temperature variations. Unequal temperature distribution comes from several important factors. One of these is the Earth's daily rotation about its axis. Another is the change of seasons as the Earth travels around its orbit. Still another is the fact that land temperatures vary in accordance with their surfaces. Sandy areas will absorb heat faster than wooded or grassy areas, while water temperature remains fairly constant. At night, the land surface loses heat at a more rapid rate than the water surface. These temperature variations are the result of 4 individual heat processes, namely radiation, conduction, convection, and advection. Radiation is the process of heat transfer by means of electromagnetic waves. This solar radiation, or insolation, has little effect on the atmosphere as it passes through it. The Earth's surface absorbs about half of this solar energy and then gives it off in long-wave radiation. Because of its long waves, this reflected terrestrial radiation has a much greater effect on the atmosphere, which may absorb as much as 85% of the heat. The unequal heating of land and water surfaces by radiation results in conduction, a process by which the air is heated through contact with a warmer surface. The air temperature directly above the land and water surfaces will increase during the daytime as the surface temperatures are increased through the sun's radiation. At night, as the Earth loses its heat by terrestrial radiation, the air will cool by contact with the colder surface, unless a layer of clouds is present, which will act as a blanket and slow down the rate of cooling by reflecting some of the terrestrial radiation back to the surface. This is known as the greenhouse effect. As the air temperature increases, the air expands and begins to rise, producing convection. The cooler air from surrounding areas will move in and replace the air that is rising, producing advection. When advection takes place, it can be in the form of warm air advection or cold air advection. A good example of warm air advection is the flow of air from the Gulf of Mexico to the southwestern portion of the United States. This generally produces adverse weather conditions. Cold, dry air from the north generally produces good flying weather. A result of this uneven heating is a pressure and wind circulation pattern in the northern hemisphere known as the primary circulation. The intense heating and advection of the air at the equator causes the air to rise. This creates a low-pressure belt that extends around the Earth's surface in that region. Some air cools and descends near 30 degrees north latitude. Some continues to the polar region and descends. As a consequence, higher pressures are built up in both of these general areas. However, at 60 degrees north latitude, polar air moving southward over the Earth converges with the warm air moving north. The warmer air rises and results in relatively lower pressure in this vicinity. The high and low pressure systems shown on the surface weather map are known as the secondary circulation. A high pressure system is also known as an anticyclone. Within this pressure system, the wind flow is clockwise and parallel to the isobars above 2,000 feet. A low pressure system is also known as a cyclone. Within this system, the wind flow is counterclockwise and parallel to the isobars above 2,000 feet. Below 2,000 feet, friction causes the air to flow across the isobars at about a 30-degree angle toward lower pressure. This causes a convergence and lifting of air near the center of the low pressure, and a divergence and sinking of air near the center of the high. High pressures or low pressures, rising or falling temperatures, increasing or decreasing water vapor content. These are the principal weather factors which separate the dynamic changing troposphere from the serene, undisturbed stratosphere. But we live in the troposphere, and for a long time to come, we'll do most of our flying there. This is why it is so important for every Army aviator and every flight operations specialist who works with him to understand some of the principles behind these factors and some of the results, the hazards they can bring about.